All right, we are almost done. There is one last result that I want to prove about uniformly continuous functions. And that is the fact that if you have a uniformly continuous function and you take a limit point of the domain of that uniformly continuous function, then this limit exists. Now, to motivate why this should be surprising, let's think about a continuous function. I don't know, how about this? Let's take f of x to be, I'll stick with this, the sine of 1 over x on the interval from 0 to infinity. So here, this is specifying the domain. So let's just take a glance at the graph of that function. And in fact, you know what? Let's not hand draw this graph. I'll be back with a computer-generated graph. Here we go. There's the graph of f of x equal to the sine of 1 over x from 0 to 6. And you see, if you were to want to try to take the limit of this function as x goes to 0, well, you would have trouble making sense of what it should be. By looking at the graph, it certainly isn't clear. It should apparently be, I don't know, everything between -1 and +1. So this sucker has the property that 0 is a limit point of u, but limit as x approaches 0 of this function does not exist. So continuous functions don't always have limits at their limit points. We are going to show that uniformly continuous functions do. We are going to prove the following theorem, theorem 3.8.13. Let u be a subset of R, and f from u to R be a uniformly continuous function. Let p be a limit point of u. So remember, a limit point is a point at which you can try to take a limit. Then the limit as x approaches p of f of x exists. So let's try to come up with a proof. Again, I'm going to go to the setting of sequences. So maybe I'll remind you of the sequential reformulation of limit points. So what does the sequential reformulation of limit points say? The sequential reformulation of limit points says that p is a limit point of a set u if and only if there exists a sequence x sub n of elements of u different from p such that x sub n converges to p. So just remember that. So let's do this. So let's get the setup. Let's let u be a subset of R. Let f from u to R be a uniformly continuous function. Let p be a limit point of u. We need to show that the limit as x approaches p of f of x exists. And as with lots of these existential arguments, we're going to try to come up with a candidate to be the limit of this function. And then we'll prove that this candidate is actually the limit. So it'll feel kind of like the proof that Cauchy sequences converge, right? How do we prove a Cauchy sequence converges? First we found a candidate to be the limit, then we showed that that candidate was the limit. So since p is a limit point of u, then by the sequential reformulation of limit points, which is what we just stated off to the side, there is a sequence x sub n of elements of u such that, u different from p, such that x sub n converges to p. Now, x sub n converges to p, so x sub n, well, let's read the prompt. A word that's equivalent to convergent. Well, Cauchy sequence, a Cauchy sequence being Cauchy is equivalent to that sequence being convergent. So the sequence x sub n is Cauchy. So, by the theorem that we just proved moments ago, or maybe long ago, depends on how long you take between watching these videos, the sequence f of x sub n is also Cauchy. Thus, by the Cauchy convergence theorem, since f of x sub n is Cauchy, the sequence f of x sub n is convergent. Well, now I have a candidate to be the limit. Let's let y be the limit. And let's maybe motivate why this was a reasonable thing to do. So let's see, if the limit as x approaches p of f of x, let's call it L, exists, then since x sub n converges to p and is always different from p, it must be that the limit of f of x sub n, maybe for emphasis n is going to infinity, must also be L. But this is the thing that we've already given a name to. We know that this exists. We've called it p. No, we didn't call it p, did we? The limit of f of x sub n is... the limit of f of x sub n is y. So, what's the takeaway? This means that if the limit as x approaches p of f of x exists, then it has to be equal to y. So if we want to prove that the limit exists, we may as well just show that the limit as x approaches p of f of x is y. Now that we have an actual candidate to be the limit, we just need to show that. We have a sequential reformulation of limits. We could try to cook up like an honest-to-God epsilon delta argument of what the limit is, but instead let's go for a sequential argument. So let's remember the sequential reformulation of limits. The sequential reformulation of limits. Right, what did that say? That said that the limit as x approaches p of f of x is equal to, let's even, y is the thing that we want it to be, if and only if, for every sequence x sub n of elements of the domain of f different from p, if x sub n converges to p, then f of x sub n converges to y. So now we know what we need to show. If we want to show that the limit as x approaches p of f of x is equal to y, then we need to show that for every sequence x sub n, although x sub n already has a job, right? So let's call it something else. For any sequence w sub n of elements of u different from p, if w sub n converges to p, then f of w sub n converges to y. And so now, well, we know what we need to prove. We need to prove that for every sequence of elements of u minus p, which happens to converge to p, then f of that sequence converges to y. So that tells us what we need to prove. We need to start by considering any sequence wn of elements of u minus p. We get to assume that w sub n converges to p. We need to show that f of w sub n converges to y. And there will be a bit of a trick that we'll do. So here's a sequence that we'll study. We'll take the sequence Zn, which just follows by alternating between terms of w and terms of x. So remember, xn, so off to the side, remember, this xn converges to p, and f of xn is known to converge to y. W sub n converges to p. We want to show f of w sub n converges to y. And so we'll build this sequence by alternating between the two of them. So Zn is xn over 2 when n is even, wn plus 1 over 2 if n happens to be odd. Those parentheses matter, right? I claim that this sequence converges to P. And in a normal semester, I would then ask you guys if you want to see the proof of that, but I can't do that because of the nature of reality right now. So I won't, but I will post an additional video in the sequence video, so this one won't be the last, in which I'll give the proof. Sorry, I'm making this up as I go, right? By the Cauchy convergence theorem, if I know that Zn converges to P, then I know that Zn is Cauchy. So by theorem 3.8.12, I conclude that f of Zn is Cauchy, and so is convergent. Let's let L be the limit. But then notice, f of xn is a subsequence of f of zn. If I only take the even terms of zn, whenever n is even, I get terms of xn. So if I only take the even terms of zn, I get f of xn. So f of z sub 2n is the same thing as f of xn. It's a subsequence of f of zn. So that means not p, right? The limit of f of x sub n by assumption was y, which is the limit of f of x sub n, is the same thing as the limit of f of z sub 2n. Well, that's the same thing as the limit of f of z sub n, because if you take the limit of a subsequence of a convergent sequence, you have to get the same limit. So let's put down the conclusion. Thus, y equals L. But the sequence z sub n isn't the sequence that I care about. I don't actually care about what the limit of zn is. I care about what the limit of wn is, right? If you scroll up, we consider any sequence wn of elements of u minus p and assume that wn converged to p. We needed to show that f of wn converged to y. That's what we needed. So, but wn is a subsequence of zn, so f of wn is a subsequence of f of zn, right? F of wn is f of z sub 2n minus 1. And I paused there for a moment because I had to think whether plus 1 or minus 1 was the right thing. Let's just go ahead and check. Right, if I plug 2n minus 1 in here, yeah, I get wn out. Good. So, right, it doesn't matter how it's a subsequence, so I don't actually care that this is what belongs in that subscript, but I should write something that's, not false. So since this thing is a subsequence of f of zn, we see that the limit of f of wn is the same thing as the limit of f of z sub 2n minus 1. Well, wait, that's a subsequence of f of zn. The limit of f of zn is L, or we've shown that that's the same as y. Hey, neat. We just showed that the limit of f of wn is equal to y, and that should make us happy because, if you remember what the whole goal was, we want to show that for any sequence wn of elements of u minus p, if that sequence converges to p, then f of wn converges to y, because then I'll be able to use the sequential reformulation of what the limit of a function is. And let's see if we actually did that. Well, we considered any sequence wn of elements of u minus p, and we assume that wn converges to p. So we have shown now that for any sequence wn of elements of u minus singleton p, such that w sub n converges to p, we have proven that f of w sub n converges to y. So by the sequential reformulation of limits, we see that the limit as x approaches p of f of x equals y, in particular, the limit as x approaches p of f of x exists, proving the theorem. Wonderful. So the one last video that I will produce will be a freehand video in which this claim will be proven. Great. I'll see you then. Stay safe.